Hello everyone. In this video, I'm going to talk about higher degree polynomials. I will specifically discuss how to determine the end behavior of a polynomial function, which relation exists between its real roots and its graph, and what we can know about the turning points of a polynomial function, as well as what is meant by a turning point. In the next video, I will talk about other theorems which enable us to get more information about the graph of a polynomial function. But first of all, let us do a quick refresher on what a polynomial function is, and then we continue. Alright, so a polynomial function has this form an times x to the power of n plus etc. plus a0, where n is a positive integer and an minus 1 down to a0 are real numbers, which are the coefficients of a polynomial function. The term with the highest exponent is called the leading term, the corresponding coefficient is called the leading coefficient, and n is the degree of the polynomial. For more details, you can look at the videos I previously posted on polynomial functions. Okay, so what is meant by the end behavior of a function? It simply means which value y is approaching as x approaches positive infinity and x approaches negative infinity. For example, let's say we have the following. Let us say that if x approaches minus infinity, y approaches plus infinity. What does this mean? It simply means that if x approaches minus infinity, and I'm talking about this region, y approaches positive infinity, which means the left end behavior of the graph looks something like that, and so on. Now, how can we determine the end behavior of a polynomial function given its expression? It all depends on n, which is the degree of the polynomial. So first of all, we need to know whether n is even or n is odd. If n is even, this means that both n's are the same, either positive infinity or negative infinity. In other words, either both n's are positive infinity like this, or minus infinity, something like that. In order to know whether it's positive infinity or minus infinity, we have to check the sign of an, which is the leading coefficient. If an is positive, then both n's are positive infinity, and if an is negative, then both n's are negative infinity. What if n is odd? In this case, both ends are opposite. One of the ends will be minus infinity and the other end is positive infinity. In order to know which end is what, we again have to look at the sign of an. So if an is positive, then when x approaches minus infinity, that means when x is at the very left, then y approaches minus infinity, which means y is at the very bottom, something like this. And when x approaches positive infinity, y approaches positive infinity, which means something like this. Similarly, if an is negative, then when x approaches minus infinity, y approaches positive infinity, and x approaching positive infinity gives us y approaching minus infinity, something like this. Let us now move on to the real roots of a polynomial function. First of all, we need to know that a polynomial function of degree n will have at most n real zeros, or x-intercepts. So this means that we might either have n real zeros or less. And I repeat, we are here talking about real zeros, not complex zeros, which means there is a possibility to have less than n real zeros. But if n happens to be odd, then we will definitely have at least one zero. And this is not surprising. Why? Because as we saw in the end behavior, if n is odd, then one of the end behaviors will be at the bottom and the other one will be at the top. Something like this. And since a polynomial function is continuous, which means there is no cut in the graph, then the graph will definitely intersect the x-axis at least in one point, which means we will have at least one zero in the case where n is odd. Moreover, if h is a real root of a polynomial function, then x minus h is a factor of this function. In other words, we can write f of x as x minus h times some other factor, or it could be x minus h to the power of some p, where p is a positive integer. Now let us discuss what we can know about the graph given this p. First of all, if p is equal to 1, then we say that h is a root of multiplicity 1, or simply we can say it's a single zero. Something like x minus 2, for example, into another factor, and here x minus 2 has an exponent 1. Now if this is the case, then the graph of f passes directly through the intercept, something like this. What if p is equal to 2? Then we say that h is a root of multiplicity 2, so the multiplicity is just the exponent of the factor x minus h, and in this case h is called a double zero. How does the graph look like at x equal to h in this case? It touches the x-axis at x equal to h, then changes its direction. And these are two examples. Let us assume that h is a double zero here, so either the graph moves down, then up, or goes up, then changes direction. One more case, what if p is equal to 3? Then the multiplicity is 3 and we call it a triple zero. In this case, the graph will it'll pass through the x-axis, but the difference here is that it flattens a bit on the x-axis, and this is an example. As you can see, the graph did not change its direction, but it becomes flatter a little bit here at x equal to h. Now we know how the graph looks like when p equals to 1 or 2 or 3. What if p is greater than that? Can we generalize the case? The answer is yes. In general, if p is 4, 6, 8, etc., the graph still bounces off the x-axis, but as p increases, it becomes flatter and flatter as x equals to h. Similarly, if p is 5, 7, 9, etc., again the graph will pass through the x-axis, but it becomes flatter and flatter as p increases. Let us now see some examples. This is the graph of f of x equal to x plus 1 into x squared into x minus 2 to the power of 3. Here we have 3 zeros. We have x equals to negative 1, and this is a single zero. And as you can see, the graph passes through minus 1, and it's not flat at all at x equal to negative 1, I mean at the point A. The other root is x equal to 0, and it is of multiplicity 2, and we can see that at x equal to 0 or at point B, the graph touches the x-axis, then changes its direction. It was increasing, then decreasing. The third zero is x equal to 2, and it has multiplicity 3. So, the graph does not change its direction, but what is the difference between A and C? It becomes flatter at C. That's another example. We have 4 zeros here. Let us first start with the single zeros, which are x equal to minus 1 and x equal to 2. For x equal to minus 1, I'm talking about the point A. You can see that the graph passes through the x-axis, as well as when x equal to 2, I mean at point C. Now here, when the multiplicity is equal to 1, and I'm talking about x equal to minus 1 and x equal to 2, the graph passes through the x-axis, I'm talking about points A and C, and there is no flat part on the x-axis. For x equal to 0, the multiplicity is 3, and as you can see, at point B, the graph becomes flatter and even more flat at x equal to 4, and I'm talking about point D here. Again, why? Because the multiplicity here is 5. So the higher the multiplicity, the flatter the curve. This is one more example. For x equal to 0, it's the same story as we explained before, but here I want to focus on the other zeros. So the 0 x equal to minus 3 has multiplicity 2, so the graph changes its direction at x equal to minus 3, or at point A. The same thing happens at x equal to 2, but of course the graph is clearly flatter here. Why? Because the multiplicity now is 4. One last thing I want to talk about in this video, which is the turning points. First of all, what is a turning point? It is a point where the graph of a function changes from sloping downward to sloping upward or vice versa. In other words, if you have something like this is the point where the graph changes its direction. So this is a turning point. This is another example, and here is the turning point. The graph was decreasing and then it becomes increasing. In simpler terms, it is just a local maximum or a local minimum on the graph. What we can know about the turning points of a polynomial function is the following. Any polynomial function of degree n will have at most n minus 1 turning points. Let's see some examples. Let us consider this function f of x. The degree of this function is 5. Then we will have at most 5 minus 1, which means at most 4 turning points. Let us count them. We have 1, 2, 3, and 4, and yes, we got 4 turning points. That's another example. The degree of this polynomial is 4, which means we will have at most 4 minus 1, 3 turning points. And yes, we have 1, 2, and 3 turning points. But wait a minute, can we always say that we will always have n minus 1 turning points? The answer is no. Because if you remember, we said that we will have at most n minus 1 turning points, so we might have less. And let's see an example. Let us first find the degree of this polynomial function. Here the term with the highest exponent is x cubed. Here we have x squared. And here we have x to the power of 1. So the degree is 3 plus 2 plus 1, and it's equal to 6. This means that the number of the turning points should be less or equal to 5. And yes, 1, 2, 3. We got 3 turning points, and this means that we will not necessarily end up with n minus 1 turning points. It is either n minus 1 or less. That's all what I want to talk about in this video. As I mentioned before, in the next video, I will discuss other important theorems which will help us extract more information about polynomial functions. Thank you for watching, and see you in the next video.